Hey guys, this is Dr. Wolf explaining Section 5.1, Randomness, Probability, and Simulation. So a simulation is a carefully developed plan for imitating chance behavior. We base a model that accurately reflects the random phenomenon under consideration. The chance of an outcome occurring is simply estimated after recording the results of the simulation in a frequency table. So based on that frequency table, we'll know the probability of our outcome simply by counting the number of times the outcome occurs and dividing by the total number of repetitions of the chance process. Simulations are a less expensive, less time-consuming option for estimating probabilities that come reasonably close to the truth. Now, familiar objects like coins, dice, and playing cards can be used to simulate chance behavior. So for example, let's see if we can explain how we could use coins, dice, and playing cards to simulate an outcome that has a 25% chance of occurring. So if we use coins, and we have 2 of them, then all we have to do is think about the sample space, and if something's got a 25% of chance of occurring, we can let HH equal outcome occurs and we can let H, T, T, H, T, T all represent outcome does not occur. And you can see what we did here. We have an outcome occurring 25% of the time, and we have an outcome that doesn't occur then 75% of the time. And we can do that with 2 coin flips. Okay, then we want to ask in part B, how could we do this with dice? So in order for me to squeeze this in, I'm going to have to erase part A. So for part B with dice, we have to think again about simply rolling 2 dice. So if we roll 2 dice, we think about the way we could model something that's going to happen 25% of the time, see if you could come up with this idea. If we roll 2 even numbers, the chance of that happening would be a half times a half, which is a fourth, and any other roll would be 3/4 of the time. So again, we have, using 2 dice, the ability to show an outcome that happens 25% of the time and the outcome that does not happen 75% of the time. So we have here, outcome occurs, while here, outcome doesn't occur. And again, we have the idea of 75%, 25%. Okay? Then finally, we can do the same type of thing with cards. And if we do it with cards, we'll get the idea that maybe a lot more easily that we could probably use the card suits to represent the outcome occurring or not occurring. And when we use the card suits, all we have to do is say let hearts equal outcome occurs, and we can let the other 3 suits represent the outcome that doesn't occur. And then that would mean diamonds, clubs, and spades would all equal outcome does not occur. again, we got to the idea that the outcome would occur then 25% of the time, and the outcome wouldn't occur 75% of the time. Okay, let's go to the next example. And again, I think to organize this, I'm going to have to erase. So in the next example, we give you some context. And the context is about
I'm not quite sure how to help you with that.
a stoplight. And if we look at the stoplight, it says on her drive to work, Lana passes through an intersection with a traffic light. The light has probability 1/3 of being green when she gets to the intersection. Explain how you could use these chance devices to simulate whether the light is red or green. Okay, so since we already practiced with dice and cards, let's just do part B right here. How could we use random digits? Because ultimately for the simulations that we're responsible for here, we're going to use random digits. So if we use a random digit, we need to come up and construct a scenario where 1/3 of the time the outcome happens and 2/3 of the time the outcome doesn't happen. And we're going to have to use the table of random digits. But now the random digits are 10 digits, so we have to just be a little bit clever. So let's let 0, 1, and 2 equal green light. And then we can let 3, 4, 5, 6, 7, and 8 equal red light. So then what happens when we get the 9? If we get the 9, it would mean 9 equals ignore and select another number. Another digit. So what we've done in this construction is we've given ourselves a 1/3 chance of seeing a green light using 3 digits. We used 6 digits for red light, so that's a 2/3 chance. And then we have to specify ignore the digit 9 so that we can construct a 1/3, 2/3 chance using that table of random digits. Okay, so I flipped to page 32. As I said, we're going to use the table of random digits to construct some simulations for some real-life examples. And in order for us to successfully do that, we're going to ask you to follow 5 steps. And when we ask you to follow these 5 steps, they're going to be as follows. In step 1, we're simply going to restate the problem to describe some random phenomenon of interest. In step 2, we'll state the assumptions, and in the context of the problem, we'll state the chance of observing the outcome on any given trial. In step 3, we're going to assign digits to represent those outcomes. And in step 4, this is where we do the simulation. We simulate many repetitions or trials, and in the context of a problem, we have to define a trial to consist of reading a sequence of n digits from a row in the table. When reading the digits, it's going to be important for us to say whether or not repeats should be ignored. And then we'll conduct many trials. For our purposes, usually between 10 and 30, just to demonstrate the process. Sometimes you might see me in the notes just doing 5, but in the homework, please do somewhere between 10 and 30. And then you record the results in a frequency table. Each reading of a sequence of n digits is representing one trial, not n trials. You have to read n digits to represent one trial. In some cases, n is going to be fixed, and in other cases, which are called wait time simulations, you're going to continue reading off digits on the table until some condition of interest occurs. For an example of wait time simulation, I'm going to ask you to read the textbook, example 5.6, on pages 291 and 292. And then finally, once that simulation and frequency table are done with in step 4, we have to simply state a conclusion, where we estimate the probability of our outcome by calculating a proportion or number of times the outcomes occurred divided by the total number of trials. So the most important thing is to understand the digit assignment, step 3. I figured we could practice that using the following example. So if we practice assigning digits, first scenario is, let's assume that I've got one large container of Laffy Taffies, and I'm going to blindly reach in and grab one piece. Let's model each situation below. So what you have to imagine is that I've spilled out these Taffies and I've counted them all, and I know that 30% are banana. So if I want to simulate me blindfolded reaching in and grabbing a banana, I have to assign digits. Suppose I know 30% are banana. So the most reasonable thing to assign the digits to represent the flavors of Laffy Taffy is, for 30%, I'm simply going to make a definition of, let 1, 2, 3 represent me getting a banana, flavored taffy. And then the numbers 4, 5, 6, 7, 8, 9, and 0 to mean that I did not get banana. And you can see that I have a scenario where my outcome will happen 30% of the time, and my outcome won't happen 70% of the time. So continuing with the Laffy Taffies, suppose 57%, lucky me, 57% of the Laffy Taffy jar is banana. Okay, so now I need 57 digits to represent banana, and again, I think the simplest way to do it is to say 01-57 will be banana, and the numbers 58 to 99 along with the 00 will be not banana. So I have a 7% chance of success and then a 43% chance of failure. Next, I'm going to choose banana where 1/3 are banana. So if I do the 1/3, 2/3 deal, just like the example with the traffic lights, it's going to make the most sense for me to say 1, 2, and 3 are banana. Three to 9 are not banana. And then ignore 9. Ignore 0. So I'll ignore the 0. And then finally, what if I actually am interested in not just a binomial scenario of banana, not banana, but what if I'm interested in recording the actual flavor selected out of a jar? Again, I've spilled out the jar, and I know that 10% are banana, 20% grape, 30% green apple, 40% strawberry in this particular jar that's purchased. So using these percentages, it would be a simple assignment of just the number 1 to be banana, the numbers 2 and 3 to be the flavor grape, the numbers 4, 5, 6 to be the apple flavor, and then finally 7, 8, 9, and 0 to be the strawberry flavor. Okay, so now let's get down to an example of a simulation where we can do all those 5 steps that I discussed. And what we just practiced was just step 3, using digits to represent the outcomes. So one of my favorite games, Scrabble, we know is a game where each player begins by drawing 7 tiles from a bag containing 100 tiles. In this bag, not unlike my jar of Laffy Taffy, suppose we have specifically 42 vowels, 56 consonants, and 2 blanks. Kate chooses 7 tiles and is surprised to discover that all of them are vowels. Let's try to use a simulation to see if this result is likely to happen by chance. So this idea of likely to happen by chance. Figuring out the chance of getting all 7 vowels when drawing 7 tiles out of a Scrabble bag, you might have a way to do that theoretically, and you could probably use some of the methods we taught you in Section 5.3 to figure that out. But imagine we have no thoughts about laws of probability, so we just want to estimate the chance that this happens. So to model out chance behavior with the 5-step process, here's how it would look. First, we get step 1. Step 1 is where we restate the question. So when we restate the question, we are just going to write down the question again, essentially. If you pick 7 tiles from the bag, what is the chance that all 7 are vowels? Step 2 is where we have to put some assumptions down. So the assumptions about the 100 tiles is, I guess, the breakdown of the probabilities. So we have bag is 42% vowel, 56% consonant, and 2% blank. A secondary assumption is each time we play the game and get a tray of 7 tiles would be independent of any other time we play the game and get a tray of 7 tiles. So we're going to write each tray of 7 tiles is independent. Because anytime we carry out a simulation, we must have this assumption of independent trials in the simulation. Okay, so then we have to go on to the other steps, and to do that, again, since I'm having trouble writing on this screen with this pen, I have to erase so I can fit the other steps. So I'm going to erase. Okay, so step 3 is where I assign digits. So when I get to step 3 to assign the digits, just like the Laffy Taffy example, I'm going to let 0, 1 to 42 mean that I draw a vowel. And I'm going to use 43 to 98 for the consonants. And then I'm going to use 99 and 00 for the blanks. So this is where I assign the digits. In step 4, I must describe one simulation. So for one simulation, I'm going to read 14 2-digit numbers from the table. And because I'm sampling these Scrabble tiles from the bag without replacing them, I have to write ignore repeats in the instructions for this simulation. Write ignore repeats. Okay, so that's one simulation. Described, read 14 digits, 2-digit numbers from the table, ignore repeats. Part of step 4 then is also to read those digits. So you can see that I put in above the problem right here a set of rows of random digits. So I'm going to use those rows to generate trials, which represent me drawing a tray of Scrabble tiles. So here's how that's going to look, and again, I'm going to erase. So I'm going to make a frequency table, but I'm going to put a fair amount of detail in it so you can see the process. And when I make this frequency table, I'm going to put a column heading of trial. I'm going to put that column heading down for the word trial. Trial number 1. All I have to do in this is show the digits in my tray. So let's see what my tray will look like for trial 1. So if I go up there and read 2 digits at a time, the first thing I see is 96, 67, oops, not 67. I see 96, then I see 74, 61, 21, 49, 37, and 82. And the result is what I need. I need to count how many vowels I got. So since the vowels are just the numbers from 1 to 42, I can clearly see that I got 2 vowels in that simulation. Trial number 2. All right, so just imagine this as the game starts again. It's a fresh bag of 100 tiles, and you draw out 7 again. So trial 2. Let's draw out 7 again. We pick up in the row of random digits right where we left off on the previous trial. So I have 37, 18, 68, 44, 23, 51, and 19. And I again count the vowels, and I have 4. Trial number 3. I have 62, 10, 33, 92, 44, 96, and 71. And you can see how many vowels I got, and that would be 2, once again. Trial number 4, and I'm only going to do this 5 times. So in trial 4, I have 99, 31, 36, 80, 97, 41, and 92. The vowels are 3. Trial 5, I have 77, 56, 78, 87, 41, 48, and 40. And I have 2. Alright, so that gets us up to step 5. When I get to step 5, all I have to do is figure out the probability of all 7 vowels from my frequency table. And I can see in my 30 simulations, it happened 0 out of 5 times. So I'm saying I have close to a 0% chance of a tray with all 7 vowels. So Kate, who played that game, would know that she witnessed something extremely rare to reach in a bag of 100 Scrabble tiles and find all 7 vowels. I worked out a theoretical answer behind the scenes. Behind the scenes, the theoretical answer using the multiplication rule for dependent events, you should be able to multiply 7 fractions together and get the theoretical probability of 0.0017. Alright guys, so I'm sure this video is already super long. This page right here shows some calculator commands, and there's calculator shortcuts for doing random digits. But honestly, I think this is something that we can skip for now for lack of time. So I'm going to flip this page. This next page, again, my favorite game, Scrabble. One of the other things that rarely happens is playing a game of Scrabble where you can use all 7 tiles on your tray to make a 7-letter word. So you can see the scenario here, and after the explanation, which you can read on your own, we need to figure out what's the chance that we could draw a tray of 7 letters and end up spelling a word. And we're told in the context that that happens about 3% of the time, that the first player can make a bingo and play all 7 tiles. So here's me restating the question. Here's step 2, where I must give some conditions here, the assumptions. Each trial of drawing 7 tiles from the bag is independent. On any trial, there's a 3% chance of making a 7-letter word. Step 3, if there's a 3% chance of making a 7-letter word, then when I assign digits, I'm going to represent 1 to 3 to be the outcome a 7-letter word is formed, and the tiles, the digits 4 to 100, saying that, well, we didn't make a 7-letter word. Here's me showing what I skipped on the previous page, the random integer command. I can very, very quickly get 100 trials done if I use random integers from 1 to 100 and get a list of 100 numbers in L1. When I do that, I wouldn't sort them, and I would record the number of plays it takes to see a 1, 2, or 3 in the list. The question was a little bit different. How many games would I have to play until this happens? How many games would I have to play? So when I put this random integer command of 100 numbers in a list, the 3% of the time was me waiting to see if I could get a 1, 2, or 3. Or sorry, counting, not waiting, counting until I got a 1, 2, or 3. So when I stuck those 100 numbers in a list, the very first time I did it, it was the 15th game where I spelled a word, meaning I got a 1, 2, or 3. The second time I filled in a list of 100 random numbers, I got a word, a number 1, 2, or 3 by the 8th game. 17th game, 75th game, 8th game again. So if I took those 5 numbers, added them up, and divided by 5, I got 24.6. So this lets a Scrabble player know that, at least in this estimation, about every 25 games, and again, that's a long run relative frequency interpretation of probability, that on average it takes about 25 games to be able to play Scrabble and get a 7-letter word on your first play. Okay, you guys, remaining 2 pages, I have some examples filled out. Please read them on your own. This last one about taking the train, also a very good one, all laid out for you to read on your own. That gets you to homework number 3, which is due after Thanksgiving break.